Welcome to the next lecture on wireless communications. We will continue our study of the mobile radio propagation channel. The outline of today's lecture is as follows. We will briefly summarize what we learnt in the previous lectures. We will then get a deeper understanding of the multipath channel. Then we will look at the impulse response model of the multipath channel, followed by the discrete time impulse response. So this is the outline of today's lecture. First, we start with a brief recap. We learnt in the last class that the wireless channel is primarily multipath. That is, the transmitted signal reaches the receiver not by a single path, but a number of paths, either by reflection, scattering, or diffraction. This multipath nature results in a phenomenon called fading. We then looked at the effects of fading, how it can distort the signal, what kind of a frequency modulation can happen because of fading. We then studied the Doppler shift because we are working in a mobile environment where the mobile station is allowed to move with respect to the base station. So we learnt that if the mobile station is moving with a constant velocity v at an angle theta from the incoming signal direction, then the frequency shift or the Doppler shift is given by velocity divided by the wavelength times cos theta. Then we studied delay spread, a direct outcome of a mobile channel with multipath. We saw that if you plot on the x-axis the delay and on the y-axis the signal strength, you get to see signals being reflected from close by reflectors. Then there are some signals being reflected from intermediately placed reflectors, and then some of the signals coming from far away reflectors. What happens is there is a delay spread. This delay spread results in intersymbol interference. So ISI is a direct consequence of the multipath channel. Now today we would like to look at the impulse response of the channel, how it can help us characterize the channel and analyze the channel. The small scale variations of a mobile radio signal can be directly related to the impulse response of a mobile radio channel. The impulse response is a wideband channel characterization. Please note, we are actually doing a wideband channel characterization, which means later on, based on the impulse response, we can really analyze a channel at any desired frequency band. The impulse response of a multipath channel contains all the information necessary to simulate the channel and analyze the channel. So a lot of performance analysis is done based on the impulse response of the channel. The example that we are following, the ultra wideband channel, also has its own impulse response, and a lot of analysis, performance analysis, are done based on that impulse response. What is interesting is we carry out certain measurements to determine the impulse response. How can we represent a channel simply by its impulse response? We can do so because the mobile radio channel can be modeled as a linear filter with a time varying impulse response. It's not a time invariant system, as we will soon see. The multipath channels are changing because of the position of the mobile, and hence the impulse response is time varying. It makes it interesting as well as challenging to handle the impulse response. Note that multipath fading is characterized by its impulse response, which includes the information about the relative time of the arrival of different multipath components, the signal power in the various multipath components, and the various signal phases when the delayed signals arrive at the receiver. All this is done relative to the direct wave that comes. In most cases, we do not have a direct wave. Then all the computation is done based on the multipath reflected components. If there is a mobile reception, then the relative lengths and attenuations of the various reception paths will change with time. This is obvious. We have seen it before. Today we will also see it graphically. This makes the channel time varying. Depending upon the actual location of the receiver with respect to the transmitter, the multipath components will change. It is important to observe this, and hence your impulse response must be time varying. Please remember, we have not put any restrictions on the variability of the channel. The different components which make the channel a multipath channel, that is reflectors, can themselves alter in time regardless of the motion of the mobile station. So we must have somewhere two time axes, one for the mobile station movement and one for the temporal movement of the non-static channel. Here we assume that the time variations are strictly due to the receiver motion, where t is given by the distance divided by the velocity of motion. We are considering a constant velocity. A graphical representation, the first curve plots a kind of channel response in time versus the time axis, and as you can see that it can be clubbed together with a lot of delta functions, and this is the approximate channel response in time. There is a delay spread, right? So an impulse or a very narrow pulse that is transmitted is actually received as a very broad, not a pulse, but a variation in time. In the frequency domain, it is very interesting to observe that the channel actually behaves like a frequency selective channel. It enhances certain frequencies and it suppresses other frequencies. So a typical mobile radio channel would have a frequency response something like this, and this would also change in time. So when we observe a multipath fading environment from the perspective of frequency domain, a characteristic of this multipath channel is that some frequencies are enhanced, whereas other frequencies are attenuated. Since at any distance d, which is given by the velocity times t, the received power will have combinations of different incoming signals having different propagation delays depending on the distance between the transmitter and receiver. So the propagation delays of the different multipath component is a function of d, the distance of the receiver from the transmitter. Hence the channel characteristics or the impulse response function depends strongly on d, and we will put that in an equation very soon, d being the separation between the transmitter and receiver. Let us now formulate a model. So we are interested in finding a model for the mobile radio channel as a function of time and space. Okay. This space represents the location of the receiver with respect to the transmitter. Since it is moving with a constant velocity, we can translate this space as another axis in time. Let's put a base station and a mobile station. So this mobile station is moving with a constant velocity v, and assume that this mobile station is located tentatively at a distance d from the base station. Let x of t represent the transmitter signal. So the signal being sent from the base station to the mobile station. The mobile station currently is located at a distance d, still moving with a velocity v. So what it represents, what it receives is y, which is a function of d, because it will change if you move the mobile station, and it is also a function of t. This represents the received signal at a position d. Now h dt represents the channel impulse response, which is dependent on d, clearly, because all the multipath components being received by the mobile station will change if I change my d. Yes, question?
Sir, if I have the two base station and mobile is roaming from one to the other, at that time should we consider the effect of the other base station?
Okay, the question being asked is, suppose instead of having one base station, do we consider the effects of two base stations if two base stations were present? So the answer is, the mobile will have a certain channel impulse response with respect to base station 1 and another one with respect to base station 2, because the distances d will be d1 and d2 from base station 1 and base station 2 respectively. So we will have to consider two different channel impulse responses. Now graphically, let us find out how the various multipath components are going to affect what is received and the final channel impulse response. Let us look at the same base station again a little more carefully. In the environment, we just do not have a base station, we also have some scatterers, reflectors and diffracting objects. So we have put a tree and a house here as typical reflectors. Of course, the number of reflectors and how good the reflectors are will also depend on the frequency of operation. We have put a mobile receiver into the scenario. So when the base station, as you can see, is radiating, there is a possibility that one of the waves reaches the mobile receiver through reflection 1, and we will call it as the first multipath component. Of course, there is a possibility that the signal reaches the mobile station directly, line of sight propagation, or we can have another reflection, and let us call it the third multipath component. Please note, this is true only for the receiver at a certain location d away from the base station. These multipath components will change as the mobile receiver moves. This is the multipath channel we are considering, and we are clearly trying to find out a channel impulse response for this scenario. Real life is much more complicated. There are very many more reflections. There could be a ground reflection as well. There will be diffractions, scattering effects. So let us say that the wireless multipath channel can be represented by the impulse response h, which we have seen is a function of d comma t. What is being sent from the base station is given by xt, which is being input to this channel impulse response. What we get out is y, a function of both d and t. So now we have the factor d coming into the picture. Clearly, y d comma t is nothing but xt convolved with h d comma t, which is written in the integral form as integration from minus infinity to infinity x of tau h d comma t minus tau d tau. For a causal system, h d comma t is equal to 0 for t less than 0. Hence, y d comma t, the received signal at a location d of the mobile station at any time t, is given by minus infinity to t x tau h d t minus tau d tau. So, if I have a handle on this h d comma t, then for any given signal x of t, I can probably calculate y of t. So, this is the linear time varying channel. D, please note, is the distance between the base station and the mobile station. V is the velocity. Now, this constant velocity exactly will help me remove this term d and put another time component here. So, d is given by v times t, assuming v is constant over a short time. It's a fair assumption because the short time, how short? We are talking in probably couple of microseconds. At that time, the velocity of the car might be considered as constant. So, if it is not accelerating too fast, it's a fair assumption to make. So, clearly y, which was d comma t, has been now replaced with vt comma t is equal to x tau h vt t minus tau d tau. And if you continue with this mathematics, you finally get the received signal y of t, okay, because I have removed the d part. The location of the mobile station with respect to the base station has been eliminated, because here y v t comma t is only a function of t, is nothing but xt convolved with h v t t is nothing but xt convolved with h d t. Here note x of t is the transmitted signal, y of t is the received signal, h t comma tau is the impulse response of the channel. Please note, for the first time we have a tau which represents the multipath delay of the channel for any fixed value of t. Suppose I fix the location of the mobile station with respect to base station. Still, there will be changes in the channel because the channel is not static. Those changes in the channel are being covered by the factor tau. Whereas the motion of the mobile station with respect to the base station will also affect the channel impulse response, and that is being considered and covered by t. So, finally, after all this effort, we have y of t, the received signal at the mobile station, traveling with a velocity v and located at a distance d, is equal to x of t, the transmitted signal, convolved with my impulse response for the multipath channel h t comma tau. If we can characterize, measure, estimate or predict h t comma tau, I am in business. I can use this to predict what is my received signal. Please note that the impulse response is both a function of t and tau. T represents the variations due to the motion of the mobile station. Tau represents the channel multipath delay for a fixed value of t. Okay. We will learn how to figure this parameter out, ht comma tau. Now, let us talk from the perspective of a band pass channel and then an equivalent baseband channel for the wireless mobile scenario. Let x of t be the input to ht comma tau, our channel impulse response, but in the pass band, which is nothing but the real part of hb. Subscript b is for the baseband representation, t comma tau exponential j omega c t, where omega c is 2 pi fc, fc being the carrier frequency. Yt is what we receive. This is the band pass channel impulse response model. Here yt is real part of rt e raised to j omega c t, and yt is given by convolution of xt and ht comma tau. Surely we can have an equivalent baseband channel impulse response model, which is given by the following figure. Ct is what is input to the channel. Channel baseband impulse response is half hb t comma tau, and rt is what we receive out. Rt is convolution of ct times half hb t comma tau. Here hbt and hbt are the same thing. The factor of half comes in when you bring it down to the baseband, then to conserve the energy part you have to put this half here. So let us see what we have learned so far. We have seen that RT, which is the complex envelope representation of the received signal, is given by CT, which is the complex envelope representation of the transmitted signal, convolved with half hb t comma tau, where hb t comma tau is the complex baseband impulse response. A lot of things that we learn in digital communication now can be directly used. The results can be directly used because finally we have been able to put our wireless mobile channel simply in the form of hb t comma tau. What is x of t? Is the transmitted signal, is equal to the real part of c of t, the complex envelope representation of the transmitted signal, times e raised to the power j 2 pi fct. Similarly, the received signal y of t is the real part of rt e raised to the power j 2 pi fct. All the mathematics, the derivations that we have carried out for these complex representations can now be used in our scenario. Just a quick detour, the power of a band pass signal. If xt is a band pass signal, in that case xt can be represented, as we have seen in the previous slide, as real part of ct exponential j 2 pi fct, is nothing but ct cos 2 pi fct. In that case, the average power is given by half ct absolute value squared. Let's look at a quick example here. Suppose your xt, the band pass signal, is given by a cosine 2 pi ft. Then the objective is to find out what is the average power of x of t. So P average by definition is 1 over t integration from 0 to capital T x squared t dt, where t is 1 over f. You carry down the mathematics and finally the P average comes out to be a squared by 2. Now let us look at the discrete time impulse response model of a multipath channel. Here we discretize the multipath delay axis into tau, which are equally spaced time segments, which are called excess delay bins. Let us look at this more carefully. What we want to do is to capture the multipath effect precisely. What is each multipath component doing? We receive the signal at the receiver through different delays. If we can capture the essence of these delays, if we can break up our impulse response in such a manner that I have bins, time bins, where I can capture one delay component per bin, I am through. So somehow I have to discretize in such a manner so that each multipath component can be taken in a single bin. Suppose there are n such multipath components, 0 through n minus 1. So what do we do? On the x-axis, we have the excess delay. Why do we call it the excess delay? Because this is the delay with respect to the first multipath component you get. Okay? So all of the other multipath components can be measured with respect to the first multipath component that you get. Therefore, you call the excess delay. Clearly, the first multipath component will reach the receiver with a standard delay, depending upon how far the receiver is with respect to the transmitter. On the y-axis, I have plotted the amplitude of the multipath components that I get. Please note that these columns are representing various bins. The width of the bin will be determined by what is the actual bandwidth of the signal that we are playing with. But for the sake of completeness, let's label. So the first one, tau 0, starts right in the beginning. Each bin width is delta tau. We will do an example to find out how you determine this delta tau. Right now, we are in the process of figuring out how to come up with a discrete time impulse response of a multipath channel. So we have divided the x-axis, the delay axis, into bins, each of width delta tau. The first starting point is tau 0. The first one will be delta tau. Tau 1 is equal to delta tau. Second one will be tau 2 is equal to 2 times delta tau. The ith one will be I times delta tau, and the last one will be n minus 1 times delta tau. Hopefully, in each bin, we will catch one multipath component. Now, of course, there are two other possibilities. Either we miss out certain bins, that is, we do not get any multipath component in some of the bins, or we may be unfortunate enough to have two or more multipath components coming in the same bin. So these excess delay bins can have no components, one component, or more than one component. We should choose our delta t in such a manner that typically you should have only one multipath component per bin. So for different applications, for different bandwidth, this delta tau should change. Depending on delta tau, two or more multipath signals may arrive in the same bin, and if they do, they will add vectorially, they'll combine, and then there will be an effective fading. So what signal strength we put in that particular bin will be the vector sum of all the multipath components coming in that particular bin. In this figure, let us look at graphically just two multipath components arriving at the receiver. So we have multipath component 1 and multipath component to arriving at the receiver. They will have different amplitude and they will come at different phase. The delays will also be different. So the two components emerging from the same source at the same time, but arriving at the receiver after traveling through different paths with time difference equal to Ti are being shown here. The first one is the 0th multipath component and the second one is the ith multipath component. Note both of them are at frequency Fc. If you observe, then you will see that there is clearly a phase difference and of course at path difference. If they arrive in the same bin, then you add them up vectorially and whatever you get is what you pick out of. Now elaborating on the excess delay. Excess delay is the relative delay of the ith multipath component as compared to the first arriving component. Okay. Ti represents the excess delay of the ith multipath component. The maximum excess delay is n times delta tau. This is important because this will have a direct bearing on your inter-symbol interference and hence your data rate. If your maximum excess delay is large, then you will either have to do some kind of an equalization to overcome the ISI, the inter-symbol interference, or you have to slow down your data rate or do both. This n times delta tau can be found out easily by measurement. This model, this discrete time impulse response model of a multipath channel can be used to analyze the transmitted RF signals with bandwidth less than or up to 2 over delta tau. So if you have a certain bandwidth, you can come up with a certain delta tau for that bandwidth for analysis. Once you do that, you can calculate the maximum excess delay, the excess delay, how wide are the bins, and then you can model your channel for that bandwidth only. Clearly, if you increase the bandwidth, your delta tau will also go down. So the larger the bandwidth, the narrower is the pulse you require to probe the channel. Let us take a quick example. Let us consider the IEEE 802.15.3, which is the ultra wideband standard. The frequency band allowed is 3.1 to 10.6 gigahertz. It's a whopping 7.5 gigahertz of bandwidth, which can hopefully give us hundreds of megabits per second data rate. Our job is to find out the delta tau for this scenario. Now we know that the discrete time impulse response model can be used to analyze a transmitted RF signal with bandwidth less than 2 over delta tau. Therefore, in our case, delta tau is 2 over the bandwidth is close to 2.267 picosecond, 0.267 nanoseconds. So if you have to characterize your channel, suppose you have to find out the impulse response of the channel by probing the channel using a very narrow pulse, then you have to have a pulse at least this small or smaller, right? And then of course you have to ensure that the channel bandwidth is limited to the 7.5 gigahertz. Then you can find out the discrete time impulse response model of this UWB system. In the next slide, let us look at the baseband impulse response of the multipath channel. the baseband impulse response actually captures this arrival of the various multipath components in the various bins. So this is a direct fallout of the discrete multipath channel that we have just studied. On the left hand side of the equation is H subscript B t comma tau, the baseband impulse response, is a summation. Is a summation of lot of delta functions, a lot of delayed delta functions, delta tau minus ti, coming directly from your discretized impulse response model. However, each of the delta functions are multiplied with a scaling factor ai t comma tau. The scaling factor is both a function of t, the location of the mobile station, and tau, the temporal variations in the channel. And also there is a phase factor here, e raised to j 2 pi f c tau I corresponding to the delayed tau I plus phi I, which is again a function of t comma tau. It's a very general model, it's a baseband model. So what it tells you is, tomorrow if you send a very narrow impulse, you do a channel sounding, you're trying to measure the impulse response of the channel by sending a very narrow pulse, and clearly a very narrow pulse implies a very large bandwidth. Impulse response happens to be a wide band characterization of the channel. Then what you receive is a series of impulses, okay, and each impulse will be scaled and will have a phase associated with it, and the impulses will be delayed also. Delay term, phase term, and a scaling term. What exact model you use will be dependent on what AIs are there. Normally we can put some kind of a statistics on AI, phi I, and tau I. So if I have to characterize, for example, the indoor multipath channel, I can take a lot of measurements, do some kind of a curve fitting, come up with a reasonably accurate statistical model for AI, a statistical model for phi I, and a statistical model of tau I, and I am done. Here let us elaborate. AI t comma tau is the real amplitude. Please note, it is the real amplitude of the ith multipath component at a time instant t. Tau I, which is again a function of t, is the excess delay of the ith multipath component at time t. By definition, the excess delay is with respect to the first coming multipath component. The term 2 pi f c tau I bracket t plus phi I, which is a function of t and tau, represents the phase term, which is the phase shift due to free space propagation of the ith component. It can be simply represented as theta subscript I t comma tau. Delta is the unit impulse function. Okay. So this is directly following from the discrete time impulse response of the multipath channel. Now let us represent the H subscript B t comma tau, the impulse response, explicitly in terms of the two time axes. So what is going on? Let us put on the z axis our channel impulse response H subscript B t comma tau. It is a function of t. So if you can see, this is my t axis, and this represents the current location of my mobile station. If I am working in a fixed mobile scenario, for example, a local wireless area network, or if I am looking at a WLAN inside a room, my transmitter and receiver are not shifting with respect to each other. Then I can pick one certain location on this t-axis. So for every location on the t-axis, I have a variation of tau. So this is tau as a function of t0, tau at t1, tau at t2. And what is this tau? This tells me that, well, because of the multipath 1, 2, 3 and so on and so forth, I receive multiple delayed impulses. Please note, each one is scaled, delayed, and the phase information is not clearly represented in this diagram, but there will be a phase term also. Also note that certain bins, you do not have any multipath components, like here, here, here. You do not have multipath components coming. At time instant t0, you did obtain a multipath component at location 1, but not at tau 2, whereas after a certain time, when the mobile has progressed a little further, I now have a multipath component at tau 2. Again here and here. So it will be nice to plot a 3D mesh to see how your HB t comma tau changes as we move along the time axis with respect to tau. If we have it, we know everything about the channel. We can convolve the transmitted signal x of t with HB t comma tau, and we obtain y of t. Okay. So let us summarize today's lecture, which has primarily focused on the impulse response of a wireless channel. We first delved deeper into the multipath channel. We tried to understand how it works. Then we looked at a very simplistic impulse response model of the multipath channel. Later on, we talked about the discrete time impulse response. We will conclude our lecture here, and will continue from the next lecture. Thank you.